Good afternoon. Welcome to this month's CAPE Advanced Technology Lecture. My name is Daping Chu. I'm the director of CAPE. Today, we are very pleased that we have managed to invite Dr. Shery Huang to give a talk about her latest result and her vision about how to take it further in the area of bioengineering, which is a topic we're all very interested into, and we want not only our researchers, but our industrial partners want to take that route. Dr. Shery Huang is currently an associate professor in bioengineering in the Department of Engineering and a fellow of Homerton College at the University of Cambridge. She completed her MEng degree in material science and engineering from Imperial College, and then a PhD degree in physics from Cambridge. She is a recipient of an ERC starting grant and a fellow of the Institute of the Materials, Minerals, and Mining. The title of her talk today is 3D printing and biofabrication for healthcare and sustainability, or sustainability. Yeah, I think I got right. Thank you. Shery, please.
Yeah, thank you very much, Professor Chu. So I shall share screen.
Yes.
Yeah.
Yeah, I can see it.
Yeah, okay. Thank you very much. So yes, good afternoon, everyone. So thank you very much for joining me at lunchtime. So as introduced, I'm Dr. Shery Huang. So for people kind of like in Cambridge, so and especially in Department of Engineering, some of you might know that I'm based in Nanoscience Center. So I'm very pleased that Professor Chu has also recently just moved to the Nanoscience Center. So officially I am in Division C, which is the Materials and Mechanics and Design Division. But then my work is really crossing different divisions. And I'm really glad that today I will be able to tell you about my work on 3D printing and biofabrication for healthcare and sustainability. So, right, let's see. Can I move to the next slide? Yes, okay. Right, so I will start by giving like a background overview of some of the benefits of 3D printing. So first, 3D printing enables the objects of very complex shapes to be assembled directly from digital models. And it is well known that it enables freedoms of design and customization. And especially compared to traditional manufacturing techniques such as cutting, milling, or molding, which incurs a waste and extraction costs, 3D printing is close to a net shape formation, which means that it requires less material and also producing a lot less waste. And so 3D printing is also a distributed manufacturing method. What it means that it enables shorter supply chain. And so from the product conception to also the end product, to finally deliver to the user, the supply chain is much shortened. And therefore, if we take into account all of this aspects of 3D printing, we can say that 3D printing can potentially provide a cost-effective, competitive, and also sustainable manufacturing method compared to existing manufacturing method. So like, in fact, back in 2016, I want to bring this up that like Professor Tim Mitchell, who some of you would know him, so has already given an extraordinary foresight that 3D printing can potentially transform creativity for the fourth industrial revolution. So I would say that back in 2016, many of the 3D printing technologies were still quite immature, and their applications, as you may know, are all restricted to making prototypes or for rapid testing of product ideas. So this is creating prototypes is quite far away from creating a real functional products. Now, 6 years, so now it's 2022, and 6 years since then, we now start to see a range of functional products and structures made by 3D printing and in our daily lives. These are such as like a vegan steak on the left-hand side, which we utilize for 3D food printing, and that's on the plate and sold in the restaurants. And they are such as like the air cabin interiors that you saw here is actually flying in mid-air. So that's made by plastic printing and then coat a surface of like a gold, and then they made it really like custom designed, very pretty interiors. And lastly, on the like sort of your right-hand side, you can see buildings and bridges are now made by 3D printing. And in this particular case, it's the metal printing. Right, if we can see that like all of these achievements would have started in the laboratory. So here in this slide, I'm showing you the common 3D printing techniques currently still used in the research and development. These are such as very commonly used fused filament deposition, where you will find in the undergraduate lab, and also selective laser sintering for printing. For example, here in this case would be like a turbine blade, and then stereolithography or SLA. And then at the lower row, you can see inkjet printing, micro extrusion, and also more recently, what we called the digital light processing or volumetric printing. So for all of these techniques, we have to say that the printing process will involve the material that go through from liquid to solid transition. So this is actually underpinning all the 3D printing technology, where the material has to undergo liquid to solid transition. And therefore, when the material is in a semi-liquid state, the material can be easily and permanently molded and deformed. And once the target shape is formed, the shape has to be fixed very quickly by solidification of the material. Now, the question always comes is that what is the best 3D printing technique? In my opinion, it has to be fit for purpose. The choice of 3D printing technique has to depend on the material, structure, and the resolution required. And so this comes to sort of what's the focus of my lab and the materials we work on in my lab. So our laboratory is focused on soft, green, bio, and living materials. So for soft material, you might imagine that they behave like jelly. So what you eat, my children love jelly, so we make jellies, and they're very soft. They are viscoelastic. They have got low Young's modulus, right? And then moving on, a more complex structure is basically sort of plant extracted material, so what I call the green materials. And these materials are naturally derived, and therefore their properties are strongly dependent on where you extract them or the origin. Okay, and these materials can be heterogeneous and have anisotropic microstructures. And this is very much unlike the jelly. On the left-hand side, the jelly is basically isotropic and homogeneous. But then when you're dealing with like self-assembled structure, they're usually heterogeneous and anisotropic. Now, finally, to the more sort of living and dynamic system, like the cells I'm showing here on the right-hand side. So the cells are dynamic, and also they're highly sensitive to their environment. And so as an example here is that the same cell, everything is the same, but you basically change the fibers that they're interacting with. The cell morphology and the cell migration dynamics are completely different, as you can see in this video. So living systems are highly sensitive to their environments. So based on our material focus, our technology development is roughly split into 4 areas in my lab. So if you first focus on the vertical axis, so the vertical axis represent our ability to do printing. So we focus on 3D printing of high resolution fibers and moving all the way to the macroscopic scale, 3D printing of soft materials. Now, on the vertical axis, this indicates our ability for bioassembly and biofabrication. And therefore, utilizing self-assembly and tissue morphogenesis, we could develop microvessel on a chip and also close to organ scale organoid on a chip for biological investigations. So for my presentation today, I will first talk about the technology development in 3D printing for soft material and also high resolution fibers. And then I will show you how these technologies can be applied in healthcare. and how printing can be used as an eco-friendly method for sensor fabrication. And finally, I will end my talk with biofabrication for organ on a chip. So first of all, 3D printing of soft materials. So as shown by the diagram on the left here, many of the biological tissues, if you measure their bulk mechanical property, the bulk apparent Young's modulus, they are actually very soft. So you can imagine the bones are quite stiff and perhaps the ligaments are quite stiff, but all the internal organelles, or including also the skin, they are actually very soft, have mechanical properties below 1 megapascal. Okay, so this is in comparison to what we are familiar with, the engineering material, such as titanium, or for example, metal, other metals, and also silicon material. Their Young's modulus are actually in the hundreds of gigapascal region. And so there are already many methods to actually structure stiff material. So and then our focus is really looking at how can we structure soft material like the ones that you see here, a jelly that it's actually quite hard to sustain the shape of the jelly. And it's important to know that many groups around the world have pioneered different 3D printing techniques to structure soft materials as listed in the references here. And in my group, we recognize that we will need open design platforms to further advance the fabrication of soft material architecture. And therefore, what the unique aspect we did is actually to develop a hackable, and in another way, an open design platform that is multifunctional. And with this, we give you a nickname of printer HN. So H stands for hackable and N stands for multifunctional. So in printer HM, it has got multiple print head modules, and this is established based on a robotic arm. And altogether, this structure can be used for heterogeneous materials printing. And there's something very interesting here in our field is called the ink printability. And the printability of the ink can be tuned by different methods, including, for example, UV and also heating. And so in the case here, we established UV also heating modules in our printer. And we develop software systems associated with printer that is designed to accept different geometrical inputs, including equation, computer-aided design, CAD, pictures, and also coordinates. And this is important because different types of geometrical input will allow us to create different types of structures. So the printer is has got multi-functions because we can actually program them in an open source platform. So, and here is demonstrating the operations such as liquid dispensing, non-planar printing, and also pick and place of mesoscopic objects. And so finally, of course, we are really focusing on the price tag. So how much saving can we have if we actually going to build this printer by ourselves? So just to say, building like a version of this multifunctional printer is between £900 to about £2,000. And so if you imagine if you go out and get like a commercially available bio printer, at least you need to pay about 60K. Okay, so it's basically a fraction of price we can do it ourselves. And plus the major benefit is that this platform is modular and this platform is open to adaptation. Right, so to illustrate the benefits of having like a tunable print path, in particular for soft robotic application, we demonstrate the creation of like a soft morphing system made of a pH responsible hydrogel. So as shown in the snapshot of the videos here, so if we print the print path in different configuration, even for the same planar structure, we can have very different actuation of this planar structure. So now take these features into like a more like a structural configuration. So that's what you see here. So now we we made a print into a flower shape, and then the flower can be made open or closed reversibly in response to the environment changes as shown in these two videos here. So it's very interesting is that for the same structure, depending on the print path, you can actually tailor the application of the soft robot. So just to say the same printer setup. So we're still putting this manuscript together, but has already contributed to the work recently published by Silvia Vigolini's group. So on 3D printing of a photonic hydrogel. So Silvia's group developed this photonic hydrogel, which is based on the liquid crystalline hydroxypropyl cellulose, or HPC. So HPC is a plant-based photonic hydrogel that can be UV cross-linked. And so in our lab, by programming the printer parameters, we were able to make a range of structures like this gecko here, which shows very amazingly vibrant colors. So, and the color will be different depending on which angle you look at the gecko. So basically, the color is due to the structural reflection. So with this, I would like to give a brief summary of the first session of my talk. So basically, we developed a 3D printer which is low cost, modular, and open source. And this printer is multifunctional and is compatible with a range of materials, especially for soft, biological, and sustainable materials. So just to say, I'm very happy to collaborate with anyone you have in mind for this application. So moving on, I will take you through the evolution of fiber printing technologies that developed in my lab. In 2012, when I was a research fellow, so a collaboration with the Nanoscience Center resulted in this very interesting work of direct writing composite microfiber electrodes. And I was especially intrigued by the fiber direct writing method because it's room temperature direct deposition, which avoids the use of energy and time in intensive fabrication. However, one of the major drawbacks back then is basically we still need to use a high voltage, about 1 kilovolt, to initiate the jet. So after I established my independent group in 2016, we developed a new process called the low voltage electrospinning, which decreases the operation voltage from over kilovolts to about 100 volts. Here, what I'm showing you here is that I combine low voltage electrospinning and 3D plastic printing. So we can start to design fiber patterns through a CAD file like conventional 3D printing. And so this is a new process flow called additive batch electrospinning. So the benefit of using solution fiber printing is that potentially you can really use a wide range of functional materials. So a couple of examples shown here is our ability to enhance the fiber biologic property for supporting specialized cell growth, in this case, glomerular cells. So the fibers are mixed with decellularized matrices and spun into fibers of different mesh size. And we can then guide the cellular behaviors by changing this material composition and also material morphology. The next fiber production technique developed in my lab is called the dynamic near field electrospinning, or DNFES. In this process, the distribution of static field induces a dynamic switching between linear jetting and also controlled whipping. And therefore, it can produce a suspended piezoelectric mesh bonding to two sides of the contact. And we can also in situ pull this piezoelectric material. So we use these nanofibers to create a spider-inspired non-resonant acoustic sensor. As shown by this New Scientist article, that spider webs may act as the most sensitive ears in the known natural world. And this is because the thin, high aspect ratio of the suspended nature of the spider fibers. And now, how can we make use of the acoustic property of the spider web? We really need to convert the signals between vibration to electrical. And by using the piezoelectric properties of the fibers, and this is exactly what we did, is basically the sound pulse on the fiber, then convert into the fiber vibration and then to electrical energy. And the sensor has got very high sensitivity and energy conversion efficiency throughout the audible sound spectrum. And most importantly, this is achieved at a hearing safe loudness level, which is a big advantage compared to established polymer fiber structures. And working with Clemens Kaminsky's group, we use our fiber printing process to guide the self-assembly and patterning of amyloid fibers. The structural control of these fibers is actually more challenging because amyloid fibers is constantly aggregating. And therefore, we design a core shell flow nozzle to achieve controlled aggregation of the fibers. And we show that the fiber printing technique is able to retain the intrinsic fluorescence that's arising through the amyloid beta shaped protein folding structure. So with a core shell flow, then we can start to tune the mechanical properties of the fiber at a single fiber level. In a blended state, as you can see here, the fiber is very brittle, but in the core shell state, the fiber is elastic and also could be ductile. And with this, we can start to have bringing nanoscale self-assembly up to centimeter scale long fibers with bulk performance. So beyond tuning materials in the single fiber, we realized that connection of fibers to devices could be a major challenge because the fibers are really fragile. How can you actually put them on a device? And therefore, more recently, we created a process called the in-flight fluidic fiber printing, or IFP. So the advantage of IFP is that it combines fiber synthesis, patterning, and contact bonding in a single step. And this is also performed without any voltage application. So using this technique, we show the printing of silver fibers, and we can form sort of the layered 3D optoelectronic architecture, such shown here. And because we don't use any substrates and it's purely suspended silver fibers, it's highly transparent without any reflections that normally incur with a substrate supported transparent conducting structure. So a further ability of IFP is to interconnect fibers of very different properties. Here, inorganic fibers represented by silver can be connected in a homojunction, or alternatively, we can connect heterojunction between silver and also p-PSSS. So it's basically organic connection between the two fibers. And this is by exploiting a small voltage application to pull the semi-solidified fiber in the second layer to the first layer. And in collaboration with George Malari's group, we produced p-PSS fibers, which were shown to guide cell attachment and alignment. The fibers retain stable and functional in cell culture media for over 3 weeks. And we use this system to form an impedance sensor to monitor the cell dynamics. Here, if I can play this video again, so the fibers, okay. So basically, you can see that the cells are aligned to the fibers, and also the impedance signal actually can follow with respect to the live cell imaging data. And so we can see that in the future, this could be very useful for in vitro device modeling. So now, again, I would like to have a small section summary. So if you recall at the beginning of the presentation, we said that the choice of 3D printing technique has to be fit for purpose. And this depends on the material, structure, and resolution requirements. And as you can see here, if I plot the different 3D printing technique together in this diagram, and as you can see, our fiber printing technique actually sits very uniquely in the space where bridging the self-assembly scale and also the single cell scale. And therefore, I hope to see this technique to be useful for future to intertwine bioelectronic elements with biology. So for the next part of my talk, I would like to show how these printing technologies can be applied in a healthcare context and how fiber printing can underpin future eco-friendly sensor fabrication. So for the first study, I would like to talk about 3D printing to create biomimetic cochlear and also its integration with machine learning. And this work was performed in collaboration with Professor Manuel Benz from the Edinburgh Hospital. And I would like to show you a short introduction video as a start. Yes. Okay, so thanks for sticking to the introduction video, and I hope you like the music as well. So, okay, so back to sort of more scientific discussion. So on the top here, this shows, this is a flowchart showing the standard of care for clinical procedure for cochlear implant patients. And so now for producing a model that we would like to evaluate how electroanatomy of the cochlear patients actually affects the EFI. So this is EFI, and this is the electroanatomy. And there are two major challenges as shown here. So first, basically, is the low resolution of the clinical CT. So here is basically the clinical CT, which cannot resolve any details. Well, most of the details cannot be shown on the preclinical CT scan. And so to tackle this problem, what we did is that instead of following the conventional wisdom of reconstructing the whole CT scan in the printing, what we did is to use 4 geometric parameters to define the shape of the cochlea. And so the second problem is the fact that we don't know the electrical property of the cochlear tissue, or more precisely, it's the impedance. We don't know the impedance property of the cochlear tissue. And therefore, we choose to replicate as wide range as possible, sort of the human bone electrical impedance values, and especially we focus on the impedance value of the scalp. So with this library, so of over 80 biomimetic cochlea with them printed, and which could capture sort of the diverse geometries of the human cochlea. And also we incorporate different resistivity in this cochlear model. Then we measure EFI in the biomimetic cochlea by inserting a clinical cochlear implant. And with this, we can then establish a neural network machine learning model to learn how the different parameters of the electroanatomy of the human cochlea, or the modeling in this case, could affect the EFI. So we call this entire process 3D printing neural network co-modeling, or 3PNN. So here are selected results and performance of 3PNN. First, the 3D printing model can reproduce a wide range of clinically observed EFI without any model adjustment. So this is important. It is an autonomous prediction without any model adjustment. A further application is that we can actually use on-demand printing and actually inverse predict the patient's cochlear geometry. And because due to ethical restrictions, it is often not possible to have paired patient CT scan and EFI data, because this is actually then the patient's identity could be revealed. However, simply based on the patient's EFI, we could guess in a very probable way was the most likely geometry of the patient's cochlea. And therefore, here is what we did is basically taking the patient's EFI, and then we guessed the patient cochlear geometry only using 5 parameters. And so we can reprint this cochlea in the 3D model, and then we measure them is highly similar to the original EFI of the patients. So sort of having all this together, and this comes to the perspective. So I think there's no doubt that in the future, healthcare will be heavily relied on data, and artificial intelligence for data analysis will be central to a cost-effective and more precise prediction for healthcare. But AI always needs to start its learning from a good set of data. And because of patient privacy, patient safety, supplying a fully documented clinical data could be of ethical concerns. And therefore, I envisage that 3D printing to become a really powerful tool to create physical models. And these physical models could be perhaps used as a well-characterized training data set as a surrogate to clinical data for machine learning. Now, continue on the theme of future healthcare. In addition to software, what we always need to think about is basically better hardware. And one of the underpinning hardware technologies in the for future healthcare would be wearable devices. And this is for real-time collection of physiological signals. And so what I would like to propose to you that fiber printing could be a new eco-friendly way to create high-performance sensing elements for wearable devices. So why high-resolution fibers? So if you imagine a film-based device or a thick fiber, when a flow of analyte comes in, it would be blocked or redirected. So now, making these fibers very small and suspended, and now this entire system becomes permissive to flow or becoming breathable. And as some of you probably have worked with carbon nanotubes before, and having a high surface area to volume ratio will increase the device sensitivity. And finally, if we could then organize these fibers in 3D, this could give rise to 2 advantages. One is spatial mapping, and secondly, if the materials are different, and this entire structure could be multifunctional. So to demonstrate the starting of the proof of concept, so what we did here is using IFP, which I introduced you before, to create a sensing device. Here, what we did is to use PEDOT-PSS fibers because it's moisture sensitive. And the PEDOT-PSS fibers are basically suspended on a frame, so you can't really see the fibers here because it's so small. And we use this device to measure the breath leakages from an N95 mask. So, and due to the small diameter or suspended nature of the fiber, we found that this sensor is at least 6 times has at least 6 times better response than a commercial sensor. And here is an example that where Andy, the first author of this paper, is actually performing rapid breathing, okay, in the mask. And you can see that our sensor was able to pick up the individual breaths, but not the commercial sensor. Now, by stacking the fibers in sort of layers and having different fiber material in different layers, then multimodal and spatial sensing can be designed. Again, as an example, what we demonstrated here in this paper is that we stacked the piezoelectric fiber and also the PEDOT-PSS fiber together, and therefore sound information and also respiratory moisture information can be collected. So here, attach this sensor to the phone because this whole system is transparent, highly permissive, and different types of data, imaging, sound, and also moisture data can all be collected at the same time. And also we can put them at different positions of the mask, upper, front, back to acquire the spatial information. And so this is still like quite like a prototype or proof of concept, but this really illustrates the potential application in complementary and multimodal sensing using a single pulse of analyte. So in addition to sort of performance matrices, and what I will really iterate and also come back to the main advantage of the fiber printing technique is that it's mild fabrication. So we normally only use ambient conditions to do the fabrications, and there's no clean room required. And our technique also supports the fiber synthesis, patterning, and bonding in a single step. So like coming to the fact that there has been increased awareness of the impacts of human activities on our planet. And so we might really need to rethink about some of the processes we have been accustomed to making sensor devices. So for example, the heavy reliance on clean room, or for example, if we are gonna make e-garments, and then the dyeing process and coating process could create quite a lot of waste, and also also emissions. Okay, so I feel that so the fiber printing technologies that are demonstrated cannot replace everything. Of course, it again coming back to the fit for purpose technique, but then some of these sensors can potentially made by the fiber printing techniques, which especially is important for sort of disposable and accurate use sensors. Therefore, the ongoing interest of my lab is really to make fiber printing not only more functional, but more friendly to the natural environments and animals. So as I'm showing here, so it's unpublished data yet, but what you can see is that a bug can freely move around during the fiber deposition process. And of course, later on, so the bug is just happened to be there. We did not intend to have the bug there originally, and then we release the bug. So, and on the image here, you can see just about to see the really fine mesh of printed sensor fibers that's covering the dandelion. So it is so delicate and so like it's just so mild. The process, it did not compress the dandelion hair. Okay, so take a sort of like a break, and then for me, but anyway, so finally, I would like to spend just a few minutes on the topic of biofabrication for organ-on-a-chip. So our biofabrication capability, as described before, is shown in this horizontal axis. And just bear in mind that now we are working with dynamic and living system. And what the principle that I have is that we really need to guide the cells rather than force the cells to do what they want to do. And therefore here we did not use printing at all. So in the following results I'm showing here, I've used a mixture of soft lithography and also molding technique rather than 3D printing to create these structures. And I'm going to tell you a little bit about microfluidics for microvessel on a chip and also organoid engineering. So this is the microfluidic device that's made in my lab. It has got 6 channels and a gel compartment. And in one of the channels, we can actually form a vessel, okay? And this vessel can then be perfused and injected cancer cells into the vessel. What we can observe is the endothelial, the cancer cell interaction with the endothelial layer and also the cancer extravasation process. And we also developed an image analysis program to monitor this, this process. So using this system, we proceed to study how different combinations of endothelial cells and also brain cells, brain cancer cells and neural stem cells, and also patient-derived glioma cells can influence the behavior of the in vitro model. So towards a glioma on a chip. So this is by performing RNA analysis of the vessel, measuring vessel permeability, and also performing image analysis of the glioma stem cell migration. So with more detail, you can have a look at our publication in a lab on chip. So in a separate study, so working with Juhi Lee's group from the Stem Cell Institute, we also constructed a more complex structure using airway organoids. So airway organoids started to basically, it's like a round ball of about 100 microns. So it's very small. It doesn't have the anatomy similar to like a branching tract here. But using a new process that described in our publication here, what we show that we can fuse the different organoids together and start to form branching structures that's more similar to the anatomy of a physiological airway structure. What we show further is that by making an organoid tube of a size similar to the mouse trachea, so this is about 300 times the starting organoid size, and we can start to perfuse this microorganoid structure. As you can see, the tube, it exacerbated cyclic lumen expansion and relaxation in response to the input flow. So I hope that this biofabrication ability could open up the potential for next generation of drug screening for our fundamental biological studies. Okay, so actually this leads to the summary of the entire talk today. So just to recap the main focus of my lab. So my lab works with materials that's soft, green, bio, and living. And we develop 3D printing capabilities for high resolution fibers and also for soft materials. And we also develop biofabrication methods and to investigate the use of self-assembly and morphogenesis for microvessel on a chip and also organoid on a chip. So overall, sort of the philosophy guiding the group, my group's research is that we hope to continuously learn from biology and natural matters so that we can make functional materials and structures with minimal ecological footprints. I think that's very important that what we make engineering-wise is sustainable and healthy for a healthy future, not just physically, but also like mentally as well. And to me, it's very important to actually incorporate the living system into the consideration and also having minimal environmental footprint when we are developing new engineering technologies. Okay, so with this, I would like to thank, of course, my wonderful group. I saw the links, some of them of you are here, and really thank you very much for your contributions. And I will also like to thank my collaborators. And so, and of course, I would like to thank the funding supports provided by different funding agents and charities. And thank you for your attention.
Thank you very much, Shery. It's a wonderful talk and a fascinating work. I think it covers quite a lot of topics, a wide range, from the concepts to the methods and to the results. I'm sure there will be many questions. So now the floor is open. People can ask directly, unmute yourself, ask online, or send the messages through the chat. Are there any questions?
It's okay. If you're too shy, it's fine. Just let me know.
Shery, I'm fascinated by the things you are now building of living things towards living things. Yeah, it's not just a biological or digestible, but the living things. And I saw some signs that your printouts think people are doing meat, even vegetables started from the plants or the things. Could you elaborate a little bit on that? Because I think this is not just putting materials together or putting material together cleverly, but also maybe need certain triggers to make it into life or to things. What is the?
Yeah, I think this is like I think it's a very yes, inspiring question that the field is actually trying to address is that the engineering might not be, the biology is always like quite unexpected sometimes. And yes, and so therefore I think alternatively to address your question is that we just need to go through a trial error process And with the data set, we use machine learning to deduce the rule.
Mm-hmm.
So yeah, we just need a very big sample, because sometimes the hypothesis a lot of times doesn't go straight there. And engineering is basically a very controlled system. But it's good that we now have the engineering capability to vary a lot of parameter space.
Yes. Yes. Now, people have a comment, say it's a fascinating, a very interesting work, and maybe other comments or suggestions. Okay, I think probably people are a bit shy online or not feel comfortable about asking directly. You can do it after the talk, and you can email Dr. Huang directly or through the CAPE office. Also, the talk itself we'll try to put it online after going through Dr. Huang and then make it available. So taking this opportunity, I just want to thank Dr. Huang again for this fascinating talk and for everybody participating in it. Then the next talk in March will be on Wednesday again, on 30th of March, will be given by Dr. Jennifer Schooling from the Center of Smart Infrastructure and Construction at Cambridge. The title of the talk will be Developments in Smart Infrastructure and Construction. So thank you, Dr. Huang, and look forward to see everybody again next time. Thank you.
Thank you very much, Professor Chu. See you.
Thank you.
Thank you, everyone. Bye.
Bye-bye.
Thank you. Bye-bye.
Bye.
That's wonderful. Yeah.
Thank you.
Thank
Thank
you.
you.
Okay. How do I?
A lot of thank you messages through. Yeah.
Bye.